So let's say we're given two lines. We're given the line L1 with the following parameterization: x equals 1 plus t, y equals negative 2 plus 3t, and z equals 4 minus t. And then we're given a second line, L2. And that line looks like this: x equals 2s, y equals 3 plus s, and z equals negative 3 plus 4s. Okay. And our goal here is to find the distance between these two lines. Okay? So the claim is that if you have two lines that are not intersecting each other in the 3D space, then you could think of those lines as lying in two parallel planes. So I guess you could say it this way. These lines L1 and L2 don't intersect. They can be viewed as lying in two parallel planes. So let's think of L1 will be in plane 1, we'll call it. And L2 is going to be in plane 2. And plane 1 and plane 2 are chosen in a very special way. They're chosen so that they're parallel to each other. Okay? And that's sort of that's the first sort of belief you have to have, that can be done. Okay? Now, if you wanted to justify that could happen, I mean, we could sort of do what, if we give it a little bit of thought, these two lines have direction vectors. If we found the cross product of those direction vectors, we would get a vector perpendicular to both lines. So just make a plane that has one of the points of L1 on it with that new normal vector we just created, and then make another plane that has one of the points in L2 on it with that new normal vector, right? And you would get the equation of both parallel planes. Actually, it might be fun to do. We could do that right now if we wanted to. Ready? We can actually find an equation for plane 1 and plane 2. So let's do that instead. All right. So if I want to find the equation of plane 1, I need two things. I need a normal vector to that plane, and I need a point on that plane. So I think it's easier to just get a point. A point on plane 1 must be on line 1 by definition, because we said plane 1 contains line 1, right? So I'm just going to say let t equals 0. Let the scalar for the line equal 0. And if I plug t equals 0 in all these locations, I get back the point 1, negative 2, 4. So that tells us that 1, negative 2, 4 is on plane 1, because it's on line 1. Right? So we can start to write our equation. Our equation's going to look like this. Blank x minus 1 plus blank y plus 2 plus blank z minus 4 equals 0. And the blanks would be the components of the normal vector. Now, we can get that normal vector, and the reason we can is because we've insisted that plane 1 and plane 2 are parallel. And if plane 1 and plane 2 are parallel, and they contain line 1 and line 2, then the direction vector of line 1 and the direction vector of line 2 both have to be perpendicular to the normal vector of both planes. So I can get that normal vector by doing the following. I can take the direction vector, I'll call it V1 for line 1 there. I can cross it with the direction vector of line 2. And that will become the normal vector of both plane 1 and plane 2. Do this. We actually know vector V1. Vector V1 is right here. Here it is. It's 1, 3, and there's that negative 1 there. So V1 is 1, 3, negative 1. Cross. And if we go look at the other equation of the line, here's the other direction vector. 2, there's a 1 in front of that S, and then a 4. So 2, 1, 4. All right, so let's go do some simple math. At this point, after all this difficult thinking, I would love to do a cross product. Nice mechanical stuff. Here we go. So it's going to be I times 3, negative 1, 1, 4, minus j times its minor, 1, 2, negative 1, 4, plus k times its minor, which is going to be 1, 3, 2, 1. All righty. So what does this give us? It gives us the vector. This is going to be, if we start doing our multiplying here, our little determinants, it's going to be 12 minus negative 1, or 13, I think. You're going to have here 4 minus negative 2 would be 6, but then it's going to be negative, so it's going to be negative 6. And then lastly, you're going to have 1 minus 6, which is negative 5. So there you go. This is the normal vector to both planes, or you can call it the common normal. All right? So now we actually know plane 1, don't we? Plane 1, there it was. I had written it out. I just didn't have the components in there, but now I know what they are. They are 13, negative 6, and negative 5. So I can go plug those in. So here's 13, negative 6, and negative 5. And that's the equation of plane 1. Okay? Well, for plane 2, it's not nearly as difficult to figure this out because we actually already know the normal vector. We just need a point on plane 2. So let's remind ourselves of something. Here are the equations of the lines. Here's the equation of line 2. I'm going to take this to a new page, paste it. I know that the normal vector to plane 2, the normal vector has to be this 13, negative 6, negative 5. And if I just let s equals 0, I'll get a point on line 1. Right? So if s equals 0, I get x equals 0, y equals 3, and z equals negative 3. So this implies that the point 0, 3, negative 3 is on line 1, which is on plane, oh, I should say, be careful about that, not line 1, line 2, my bad. Line 2, which is on plane 2. The equation of plane 2 now has to be 13 times x minus 0, really. I'll write it just for now. Minus 6 times y minus 3, minus 5 times z minus negative 3, or z plus 3, has to equal 0. So now you have the equation of plane 2. All right, so there's plane 2. Plane 1 was the following. It was 13 times x minus 6 times y minus plus 2, that was, minus 5 times z minus 4 equals 0. So there's plane 1. And what we have now is we found two parallel planes that contain line 1 and line 2 respectively. So now, if we just know the distance between these two parallel planes, we know the distance between the lines, and we're finished. Let's just go back and double check I was consistent here. I wrote a point on plane 1 must be on line 1. I really should write this just to be consistent. I should really write this as the point that's on line 1 must be on plane 1. Okay? And therefore, when we sub in t equals 0 to the first parametric equation for line 1, we get this point, which is also on plane 1. Okay? All right. So I think we're all right now. We're ready to go. So what tools do I have? Well, we already proved we knew how to find the distance from a point to a plane. I proved that the other day. It turned out to be the absolute value of ax1 plus by1 plus cz1 plus d over the square root of a squared plus b squared plus c squared. So this gives us the distance from a point to a plane. Now, I don't have a point in a plane. I have a plane in a plane, right? But I don't have to work that hard. All I really need to do is figure out a point that's on one of the planes, right? And find the distance from that point to the other plane. So this isn't really that hard, is it now, right? For all that thinking, it's not so bad. So what do we know? We know the point 0, 3, negative 3 is on plane 2. Okay, that's how we made the plane. Well, now we're done. because that's the point. Here's the plane I want the distance to. Okay? Now, it's not quite written in this format, right? It'd be nice if it matched up a little bit better. So if you want, you could distribute these things and simplify stuff a little bit. So it kind of matches up well. Maybe you'll like that better. Who knows? So 13x minus 13 minus 6y minus 12 minus 5z plus 20 equals 0. That's really saying, let's go down a little bit. That's really saying 13x minus 6y minus 5z. You have minus 13 minus 20 minus 12 is minus 25, plus 20 would be minus 5 equals 0. So there's your equation of plane 1. We've got the point 0, 3, negative 3. It's on plane 2. We'll just sub in and get an answer. Okay, so we get 13 times 0 minus 6 times 3 minus 5 times negative 3 minus 5 over the square root of the normal vector, which is going to be, well, square root of the sum of the squares of the components of the normal vector. This plus this. Okay? So whatever that is. Don't forget to take the absolute value just in case it turns out to be negative. We get negative 18 on top, plus 15 is negative 3, right? Minus 5 is negative 8. Absolute value is 8. I'm going to have the square root of 169 plus 36 plus 25. Thanks. So this turns out to be 8 over the square root of 230. All right. So there you go.